Thank you, Marian. Hello, everyone. In the session, or kind of to start the session, I wanted to talk a little bit about how at Inspero we are implementing multi-organ system, but try to kind of respect the way to make it as scalable and simple to handle as possible. So at Inspero we are focusing on spheroids, or microtissues as we call it. These are cell aggregates, aggregated from different complexities, from different cells of origin, that are formed mainly on non-adherent surfaces like ULA plates, like hanging drops, or the plates that we provide ourselves. They can be of different complexities depending on how many cells you integrate and also how kind of you drive them into a specific disease models. So the tissue that you see here is a complex liver model, and we kind of have perfected it in a way that we can produce them in a very uniform way in a specific plate that we have with a very uniform cellular composition. The size is maintained over 4 weeks. Cell viability as well, and all the metabolic and tissue-specific functions as well. These cells, these microtissues can be used for toxicology applications, where we use them in screens where we kind of test different compounds on their toxicity using a simple ATP assay, for example, but also more complex assays. And we have shown that we can have a very high reproducibility of the results and kind of the reproducibility of these models over several runs, over a complete year, with a very high Z factor that is needed to scale up such kind of assays if you first now look at the single organ model. These microtissues can also be kind of derived into disease models, as has been seen before, by using very specific stimuli. For example, here we start with a healthy liver model and can use lipid loading to drive them into steatosis, where you can see in the tissue model below how and the lipids are accumulating in the tissue model. With inflammatory stimuli, we can get steatohepatitis, kind of the inflammation that is seen in the tissue of the Kupffer cells here, for example. And with profibrotic stimuli, we can then drive them even into more complex diseases like the fibrosis with collagen deposition that you can also see in the model. This can also be seen using different markers. So the inflammation cytokines are coming up with the TNF-alpha stimuli, as you can see on the left side. We can see the lipid loading in, for example, the triglyceride content if you compare the control conditions that has been cultured with standard conditions and the NASH conditions, where we have added these free fatty acid and the LPS stimuli. And we can then also see at 10 days after this whole protocol that we have an increased secretion of procollagen 1 in the NASH model, and we can even prevent, let's say, the induction of NASH by using specific inhibitors. When we create the platforms to build these microtissues in, we mostly impose them some specific requirements. So the plate format that we want to have needs to be robust in handling, so that we can do the medium exchanges that we can add to the compounds. It needs to be fully compatible with scalability, it needs to be accessible, and very important that we have access to a large amount of endpoints. This includes the biochemical assays, these includes NGS, but also kind of high content imaging. And of course, the most important part is to preserve the functions over a longer period of time, that we have a large experimental window. So one of the plate formats that we have created is this 384-well plate, which has all these characteristics. So it has a very special inside of the plate that allows to do the medium exchange in a very robust manner, so not lose the microtissue and to do a very precise dosing. Completely amendable to automation because it's a 384-well plate. And we have it enables us also to create this microtissue with a very high precisions and continuity over the different production runs that we have. And in these plates, and using the spheroid model, an important aspect is actually that we can use the same technology to create a lot of different of these spheroids. So these are the liver spheroids that I just have explained as one of the example. The pancreatic microtissues that we have, or tumor spheroids. And with kind of the possibility of the technology to create many different spheroid types, we quickly came also to the approach a couple of years ago to connect them in a way that we can create a more systemic approach to look at the different compounds. And if we look at multi-tissue systems, on top of the different requirements that I just explained before, I have 3 that I want to stress even more. So one of them is keep operation as simple as possible, because we are starting to use microfluidics with the different pumps and kind of different tubing, and this is something that you need to consider if you go to scaling. Second one is timing. So the different organ types might have different maturation times, say different QC protocols, etc., different media that you need maybe for the construction, and you need to time this properly, and if you combine that so that all the different tissue types are functional. And if you start to do combination, the whole over yield of your multi-tissue system is depending on every different element. These are the single tissue types that you include in the system, because if one is failing, the whole system is failing, but also on the microfluidics, on the plate format, etc. that you have. And this is why we have chosen the approach to use this scalable and very reproducible manufacturing that we have in the 96 on the 384 well plate, do an internal quality control to verify if these tissue models are functioning, and then using a transfer and putting it into a microfluidic system where we can combine the different tissue models and where they can interact in a microfluidic environment. And the platform that we have created is a microfluidic chip that is in the composition quite simple. So it has these 10 microtissue compartments that are interconnected by a linear channel. We have these 2 larger reservoirs on each side, and by tilting this platform back and forth, we can create the flow between the different tissue models. These channels are included in a polystyrene microfluidic chip in a frame, so that we have multiple of these multi-tissue systems in parallel. There is a small tilting unit that is placed directly in the incubator that then operates the chip so that the plate can be used as a standard microfluidic plate or stand plate, that you can remove it for medium exchange and place it back if you continue the culturing. So one important aspect that we had to design is this small microtissue compartment, because if you start to load microtissues, you need to care about how do I close my compartment, how do I keep it viable in there, or how can I remove the microtissue afterwards. And we created this funnel-like structure that on top has this small hydrophobic rim. So here is a hydrophobic rim, and the liquid is actually stopping there on the top and is not overflowing. And that allows us to use the liquid-air interface as actually the top of this small microtissue compartment that is just like 1 or 2 microliters in volume. And this open system allows us now to load these microtissues directly from the top and also access it after an experiment. Additionally, we have access from the top and on the bottom for imaging. There is also direct oxygen access, and the small membrane even acts as a little pump, so to create a good exchange of the liquid inside this compartment. Not to mention also that the polystyrene itself is not absorbent, so compared for PDMS that you see on the graph here on the top, we have kind of constant compound concentrations of the experiments, accessible to optics and also accessible to robotics from the top. But we still need the transfer, and the transfer is something that we had to optimize, and we have created basically a protocol using either a large Hamilton robot or also these small Opentrons robots that you might already know, where you can just pick on the left side from the plates that you have cultured which microtissues you want to transfer, and then you tell the program where to transfer him in the microfluidic plate, and this is then a completely automated process that does the pick and place with a highly flexible way how you combine the different microtissues in these microfluidic plates. So what we then started to do are different use cases, and one of them obviously is that we're working on at the moment with different collaborators is creating a metabolic multi-tissue disease model, as have been shown already in the previous talks, with kind of similar motivations, because these metabolic syndromes are an interaction of multiple different organs, mainly the fat, the pancreatic islet, and the liver. And that's why we are currently optimizing, on the one hand, the liver model, the islet model, and creating a new adipose model for such a system. And the crucial characteristics that are needed are that we are now optimizing the liver model also in relation to, let's say, the hormonal regulations of the glucose metabolism, which is not that trivial in such a small and complex system. So disease model means, for example, the reaction to glucagon and insulin upon, on the one hand, uptake of the glucose, creating specific endpoints, and the release of glucose, for example, based on insulin. On the other hand, we have the islet model very similarly, where we want to understand on how the insulin is increasing or being reduced upon stimulation of glucose. I just got to pick basically the glucose model. So using a very similar protocol that I have shown before, we are able to have this dependent secretion, this dependent uptake of glycogen, for example, and the difference of uptake of glycogen if we take a model that has been incubated forth with high glucose, high insulin stimulations, or a lean model, let's say, where we have cultured on the standard condition models, as can be seen here in these two graphs. On the right, on the left side, you kind of have the disease model, and on the right side, you have the healthy model that show differences on how glucose is released depending on the glucagon that we are actually applying to the system. Another combination model that has been done by our collaborators at ETH is that we used the liver inside the system as a metabolic organ in a prodrug activation experiment. And here what we have done is we use two different prodrugs. One is cyclophosphamide and the other one is ifosfamide, and both of them need to be metabolically activated by the liver to get active on the tumor. And interestingly is that cyclophosphamide is predominantly metabolized by 2B6 and the ifosfamide by the CYP3A4. And what we wanted to additionally see is if by ritonavir, that is in some cases also used as antiretroviral therapies, if this inhibition effects of ritonavir could affect actually the metabolic effect onto the progression of the tumor. And this is exactly what we could reproduce by combining actually the metabolically active liver model with a growing tumor in the same microfluidic system. And what you can see here is, on the one hand, the control, where you can see that the tumor is directly growing between day 0 and day 12. And if we add the compounds, cyclophosphamide and ifosfamide, we have the stagnation of the growth due to the effect of the metabolic activity of the liver and then the active metabolite that is having a cytostatic effect. And if we now add ritonavir, we see on the one hand that the growth is again getting higher because parts of the liver CYPs are inactivated, which means that we have less activation, and that's why again higher growth. And this is even more predominant if we go for ifosfamide, where the CYP3A4 is completely inhibited, which is actually the major metabolic enzyme for the compound. And this is also something that we can scale and what you can see is also by the number of data points that you can see here with the different conditions that we have, that we can really kind of scale such a system to have the correct number of replicates. Where do we go to? We use this model now to kind of create a fully scalable model. So from the chip system, we go now to a fully 384-well version, which means that we will have 24 channels to do these multi-tissue setups kind of on a standard plate format. We are using the same approach also to kind of to include immune cells. This required a re-engineering of the chip based on the same system in order that the immune cells can flow between the different microtissues without sedimentation and without getting stuck somewhere in the corner. And in another system, we even use the 384 well plate where we go less microfluidics, but just at an interaction between tumor and liver microtissues, for example, by just having an interaction of two different tissue compartments. All of them a little bit with different applications, but all of them still using kind of the requirements that I have defined in the middle of my talk. With this, I would like to end by acknowledging the islet and the liver team that are producing all the data around the models. My team more on the platform side, collaborations with ETH and the funding agency that support these different projects. Thank you very much for your attention.